Okay, the recording is started, and Kai, you can start in 2 minutes.
Okay. Okay, shall we start? Yes.
Yes, Kai, you can go on.
Okay. Video. Okay. So hello everyone. Welcome to Industry Session 3, Deep Learning and the Novel Applications. So so this session we have 5 papers. So now let's welcome the first presenter, Tong Zhang from Nanjing University of Science and Technology. He will present his paper, Cross-Graph Convolution Learning for Large-Scale Text-Picture Shopping Guide in E-Commerce Search.
Good morning. I'm Zhang Tong from Nanjing University of Science and Technology. It's a great honor to introduce our work titled Cross-Graph Convolution Learning for Large-Scale Text-Picture Shopping Guide in E-Commerce Search. I will introduce the work from 4 main parts, including introduction, the proposed framework, experiments, and conclusion. Let's start from the introduction. Nowadays, online shopping has become one of the most popular consumption fashions. But in many cases, when customers search for their designed products, the entering keywords, which are also called queries, could be very broad and ambiguous, and thus have numerous matching candidates. For example, the query term of dress is too broad to find those proper products. To offer better shopping guide, options are provided to extend the original query to be more professional shopping guide. After users click one of the options, the search engine will do search again by appending the term of clicked option to the original one. However, for these text options, it's sometimes hard for users to understand the exact meaning of some terms, such as gladiator sandals, if only given text. This may heavily degrade users' search experience. Therefore, we investigate a new service called Text Picture Shopping Guide, or TPSG, to help users better understand the exact meaning of terms. Accordingly, the text picture option containing a term together with the related picture is defined, and we call it TPO. Apparently, TPOs provide intuitive understanding of terms. Also, after changing text options into TPOs, the statistic of CTR is 13% higher. Initially, the pictures in TPOs are manually annotated and prefixed for those terms. Each term is only related to one constant picture. This makes TPO not personalized and costs a large number of labor resources. So, we decided to investigate how to automatically recommend the TPO and design the cross-graph convolutional learning framework. So, our contributions can be summarized as following. First, to the best of our knowledge, this is the first research literature to investigate the TPSG task and to deploy it to a large-scale online e-commerce platform. Second, we propose a novel cross-graph convolution algorithm to infer personalized TPOs from a great amount of data. Third, the offline and online tests on a large e-commerce platform validate the effectiveness of our proposed method. Then, we introduce our proposed framework in detail. The TPSG system is shown in the figure. For the query of dress, the search engine first generates lots of relative terms. For each term, a number of corresponding pictures are attached. The combination of these initial terms and attached pictures will produce a great number of candidate TPOs. Then, we design the framework to recommend the personalized TPOs from these candidate terms and related picture. It should be noticed that one picture term may correspond to multi-terms and pictures. And before designing the model, we first analyze the factors affecting users' preferences. As it is shown, these factors may include users' characteristics such as gender, age, and purchasing power, and the semantics of terms and visual appearance of pictures. Besides, users might care about the underlying attributes of pictures such as style, element, material, and the interaction between attributes of users and products described by the blue dotted lines in the figure should be well modeled. Based on the analysis above, considering the irregular structure of those attributes of users and the products, we introduce the graph model and design the cross-graph convolution learning architecture. The key part is the cross-graph convolution model, which will be introduced in the detail later. Besides, the query of the users, the semantics of terms, and the appearance of the product picture are all embedded into the framework and jointly modeled. The cross-graph convolution aims to model the interaction between two separate graphs. It contains two parts, named the cross-graph construction and factorized graph filtering. To construct a cross-graph from two separate graphs, we leveraged the classical Kronecker sum and developed a new parameterized Kronecker product to learn an optimal conjunctive adjacent matrix. And this is our parameterized Kronecker product, and this is the classical one. To inference and obtain the cross-graph, we conduct spectral graph filtering, which is similar with the classic graph convolution. But the difference is that we apply the spatial graph filtering on the builded cross graph. Furthermore, we leverage the property of a tensor operation and derive the factorized graph filtering. After this process, the computational complexity can be effectively reduced. Finally, to train the whole network, we imply the cross entropy with focal loss due to the class imbalance. We conduct experiments based on the data from Taobao online platform to evaluate the proposed model. We first introduce how to build the user and product graphs. For the user graph, we consider the attributes including age, gender, and purchasing power. Each one is divided into several discrete levels and represented by one hot vector. And for the product graph, attributes such as element, brand, material are considered, and each of them is embedded through one-to vector. We conduct both offline and online tests. For offline test, we use the log data from Taobao platform, 2 days of which are used for training and 1 day for testing. The whole dataset contains about 3.88 million users and 4 million TPOs. Few existing algorithms can be directly applied to TPSG task, as it is a new one. We adapt 2 deep frameworks, including DNN and GCNN, to the TPSG task as the baseline methods. Also, to evaluate our proposed parameterized Kronecker product, we additionally compare the CGCL with the non-parameterized version, named CGCL NP. NP means non-parameterized. So from the table, we can see that on all 4 metrics named hit ratio, NDCG, AUC, and GAUC, our CGCL achieves the best performance. To test the practical performance, we deploy our framework as well as the baseline methods on Taobao platform to perform online A/B test. Based on CTR and UV-CTR metrics, our CGCL model achieves the best performance. And furthermore, Figure 5 shows that the performance of our CGCL is persistently higher than those baseline methods. Besides the experimental results, we further provide some insights with some analysis. We first analyze the preferences learned by the cross-graph convolution, which is shown in Figure 6. Higher weights in both subgraphs in Figure 6 mean higher interaction between corresponding attributes. So from Figure 6, we can observe that users of different ages and purchasing powers pay much attention to style, element, and material, but less attention on brand. We also show 2 examples of personalized TPOs recommended by our algorithm. We can see that our proposed method may recommend suitable TPOs to users of different ages and different genders. Finally, we draw the conclusion. First, we investigated a new search service named TPSG and then deployed to one popular online e-commerce platform where user-friendly TPOs are designed. We propose the cross-graph convolution learning method by modeling the TPSG system into one mixed graph, together with high-efficient inference on high-dimensional tensors. The third one, the experiments of both the offline and online A/B tests demonstrate that the effectiveness of our proposed CGCL method for the personalized recommendation of TPOs. So that's all for my presentation. Thank you.
Okay, so I don't see any questions from the group chat and the Slack channel. So does anyone have questions? You can directly unmute and ask here. Okay, actually I have a question for Tong. So actually, can the model guarantee the generated text picture options like these options are describing the products along the same dimension? I mean, like they are all describing, for example, certain styles of the dress or like the season for the dress, these kind of things.
I'm sorry, I didn't catch you clearly. So could you describe it?
I mean the text picture option generated by the model, are they guaranteed to all like describing the same dimension, like the style of the dresses, for example, or like they're just some random like keyword picture combinations?
You mean the combinations of the TPO and the text and the picture?
Yeah. Are they along the same dimension?
So what? So you mean are they in the same dimension?
Yeah.
No. They are allowed to not to in the same dimension.
I see.
And we can use the graph to model them.
I see. Will this affect the user experience? Because I guess the user would expect like the options are actually, you know, telling a categorization of the whole space, right? I mean.
So sorry, really sorry, I didn't understand fully understand your question because I mean, so I don't understand the dimension of what does the dimension mean? You mean the dimension of the feature or dimension?
Yeah, dimension of the feature.
Yeah. But dimension of the features of them can be different. And you just asked about the experience, and I think that we can just influence the model based on the two different dimensions, and we can effectively learn the suitable TPOs for the users. So the difference of dimensions do not influence their experience. We can achieve effective inference.
Okay. Thank you. Is there any other questions? Okay, then if not, let's continue to the second talk. So the second presenter is Andreas Faulkner from Alibaba Group. He will present the work billing scale recommendation with heterogeneous site information at Taobao. So this is a joint work between Alibaba and the Hong Kong University of Science and Technology. Yeah, so.
Hi there. My name is Andreas Fadler, and I am going to present our paper on billion scale recommendation with heterogeneous site information at Taobao. This work was performed together with my colleagues from Alibaba, Huan Zhao, Jizhe Wang, Lifeng Wang, Pipe Huang, and in collaboration with Professor Diklon Li from the Hong Kong University of Science and Technology. So let's start with some background. Obviously, since this is a talk by Alibaba and particularly Taobao, our work deals with recommender systems. Recommender systems typically consist of two stages, matching and ranking. In the matching stage, we want to narrow down the number of candidate items from millions or maybe even much more items to thousands of candidates, which are then fed into a ranking engine in the second stage, the ranking stage, which ranks the candidates for individual users according to their individual user preferences. Now, in our paper, we present the SISG framework, SISG standing for Site Information Enhanced Skipgram. We have used this framework to compute efficiently embeddings for items and user types. This has been developed for the matching stage of the recommender system behind the Taobao mobile app homepage. This framework has also been deployed at the 2018 Double 11 Global Shopping Festival, which is one of probably the biggest global online shopping events. So that's just to mention that this is some actual very practical work that we present here. So to get a bit more concretely and into the details, our goal is to compute embedding vectors for products on Taobao, such that the cosine similarity of embedding vectors encodes item similarity. So how do we use that? Well, we select some trigger item based on past user behavior. That's done by some particularly implemented rules in the app. And then we use that trigger item as a query item and find the top k similar items, which are then passed on to the ranking engine. So our previous work in this field was the EGES model, which has been presented at KDD 18, which is based on constructing an eye-to-eye graph and then doing graph embedding using also an algorithm from the skipgram type family. We use here the term skipgram because we're not really dealing with words, but basically this whole approach has been pioneered initially with Word2Vec by Nikolov. Now, in our previous work, we faced several drawbacks. First, it was very hard to distribute and train globally, so we had to split the whole graph into several disjoint subgraphs and run it independently. So that meant that the embeddings ultimately lie in different semantic spaces, which makes it very hard, if not impossible, to compare certain items. So another drawback that we also had was that we didn't really have a way to get the user data into that model, so we couldn't address the cold start users problem. So overall, we decided to try something new, but in a similar spirit. Now, commonly, the challenges that we encounter in recommender systems is sparsity, meaning some items have very few user interactions. We have another big challenge, which are cold start items and cold start users, so that meaning completely new items for which there is no data, and cold start users for whom there's obviously no data too. And particularly in our case at Taobao, which is one of the biggest e-commerce applications worldwide, we're facing a massive scale. The number of our users and products are in the order of billions. So how can we address these problems while still ensuring that this whole entire process of computing embeddings, starting from the log data of the user data all the way to deploying it in the matching engine, can be completed within one day? So for this, we present here our solution using the SISG framework. Roughly, this framework is characterized by the following steps. We collect user behavior sequences from our logs. That gives us sequences of clicked items. To add site information and address sparsity and cold start, we enrich these sequences with user and site information, and then we run it through a relatively standard word-to-vec kind of process to get the embeddings. So that means in our case, we actually developed a custom and scalable SGNS implementation, which is able to deal with the scale at hand. So that makes it, based on this implementation of skipgram, we have a fast and easy to distribute training mechanism. So this is achieved by the two key components, which are adapted target negative sampling and a hierarchical balanced graph partition. Overall, this has the advantage, while we're not, using very fancy deep learning kind of models, we have a very practical and stable end-to-end pipeline, which also gives some excellent results online. So, to get more into details, how do we actually incorporate site information in our model? Well, we basically extend click sequences with special site information tokens. So, suppose that we have a sequence of the form item A, item B, item C. So that means the user first looked at A, then at B, then at C. So we could feed this sequence directly into some skipgram, word-to-vec, whatever you want to call it, algorithm, but that wouldn't give us anything about the site information. So what we do something very simple. We take the first item, then we add special tokens which represent the first item's site information to do the same for the other items. So in this example, if item A has category 1, 2 and brand 456, and item B has category 1, 2 and brand 457, the enriched sequence would look like that. This trick has actually used before, for instance, in a paper by Airbnb presented at KDD 17, and it works surprisingly well, as we have seen. Now, this can also be extended to get user type embeddings. Since every such sequence that we're looking at corresponds to a certain user, we can take a token for representing the type of the user and add it to the sequence. So in this case, if, for instance, the user belongs to the user type of females aged 24 to 29, we would add the token user female 24 to 29 into the sequence. So that was how we added site information. Now let's talk about what makes this actually possible in production, and that is distributed training using adapted target negative sampling. So when we started working on this, we actually had the problem that there was no publicly available skipgram implementation, at least that we were aware of, that could efficiently support a vocabulary of more than, say, 100 million items. So then what we decided to do was implement a custom tool based on an approach called target negative sampling, which is described in the paper referenced here. I think including two guys from Yahoo who worked on that. Now, the key point of target negative sampling is that we distribute the vocabulary across several workers, because depending on the embedding dimension, the storing the input and output vector for every item, site information, user type on one worker could maybe be impossible. And in order to avoid excessive communication between nodes, which would happen if one naively implements negative sampling, we actually sample negative samples from a local noise distribution. So the algorithm is presented here on the right-hand side. Basically, every worker samples pairs of tokens from sequences according to the standard ways. And then if the individual words in the pair are managed by different workers, we have a remote procedure call. And the key point of target negative sampling is that it's implemented in such a way that there's actually just one call for every sample, which is processed by two different workers. So more about these details, please refer to our paper and the paper we reference. Now, what actually becomes a big challenge once you apply this in our context is that we have a very unbalanced frequencies of items and site information token. Oops, that was too fast. Let's go back. And this leads to an extreme communication imbalance. So we had to modify the original TNS approach to keep side information tokens on every worker and sync these at regular time intervals. So that's why we named our modified approach Adapted Target Negative Sampling. So also to reduce the intranode communication, we had to make sure that sampled pairs with the high probabilities kept in the same worker. So that's where the hierarchical balanced graph partition comes in place. So what we do is we cut along the we cut the partition onto different workers along leaf categories, because most browsing sessions are limited to a specific leaf category. And then we use the hierarchical balanced graph partition to minimize the probability that a sampled pair A-B has A and B in managed by different workers. This depends on how often actually, according to our logs, users sort of hop between categories. Again, I would prefer, since we don't have much time in these presentations, that you look for the details in our paper. So now let's see what that looks like eventually. So first, a qualitative result, just to evaluate the embeddings from a sort of high-level point of view. On the left-hand side, oops, that was my screen. On the left-hand side, you can see a Disney plot of the user type embeddings that we obtained, which gives us a very nice structure in terms of the where the females are, where the different age groups in the female sector are, the different age groups in the male, so that all seems to make sense. What's very interesting is the cold start users case, where we can see here very pronounced differences between female and male and different purchasing powers. And also here's an example for cold start recommendations. So for a towel here on top, we see the items produced by the normal recommendation, and on the bottom we see the cold start recommendation, which is based only on site information tokens here. So let's look at some more quantitative results. These are the 3 data sets we've used. Obviously, they're not public since it's all data from Taobao. We have a data set with 25 million items, one with 100 million items, one with 800 million items. We basically use in production mostly data set with 100 million items, since in the homepage recommendation scenario, the pool of eligible items is not the full pool of all items. But we also train regularly on the 800 million set, so in order to provide a more or less complete set of embeddings for other users and downstream models. So those are some big numbers, and let's continue what that actually yielded in practice. So here is the results in terms of the hit rates for basic word-to-vec type skip-ram implementation, our previous model, the EG's model, and several variants of our framework, taking into account different site information for items and users. So there's a couple of comparisons that we did. And obviously in the offline case, we had some great increases in hit rates. So that made us do an online A/B test, which we can see here on the bottom left, and we actually gained a couple of percentage points in the A/B tests, about 1-2 percentage points over a very in the click-through rate CTR over a very well-tuned baseline, which is actually very, very tough to beat. So in terms of the scalability, we observed some pretty normal, pretty nice-looking scalability behavior. That's seen in the graph on the bottom right. So more workers, reduced training time, and speed also stays relatively constant in terms of tokens processed per hours. So let's go on to the final slide. So here's already the summary. We presented a very practical solution for computing embeddings at Taobao scale. It uses a simple yet flexible SGNS type model. Distributed training still challenging, but using two T components, AT and S, and hierarchical balanced graph partition, it works out and gives us a straightforward training and preprocessing pipeline. And also, we can address cold start items and cold start users problems. So that is it. Thank you very much. If you have any questions, contact me by email. I'll be happy to help. Bye.
Okay, thank you, Andreas. Is there any questions? It seems Slack channel is also very silent. Any questions? Okay, then I have a question for the presenter. So I see there are like a few very important techniques to make the training process scalable, like only thinking at regular time intervals, and also like the partitioning schema. Right. So my question is, do these optimization techniques affect the quality of the model?
Can you hear me? Yeah.
Yeah.
Well, initially, when we started this, we in the first test we saw some decrease in quality, but after a bit of hyperparameter tuning and adjusting like the sync intervals and so on, it was okay actually. So. So we usually had some small validation sets that we ran side to side, and yeah, then it was usually fine.
I see. Got it. Thank you. If there's no more questions, then let's continue to the third presentation. So before we start, actually, let me check. Is Shenxing here? Okay, seems the presenter is not here. Then we have to skip the question part and only just play the video. Okay, so basically this presentation is given by Shenxing from Nanyang Technological University. So the title is Hierarchical Bipartite Graph Neural Networks Towards Large-Scale E-commerce Applications. So this is a joint work with Alibaba Group, Central University of Finance and Economics, China, and the Zhejiang University. Okay, let's start.
Hello everyone, I am Shenxing from Nanyang Technological University. Today, I represent our team to introduce our work about hierarchical bipartite graph neural networks towards large-scale e-commerce applications. The e-commerce era is witnessing a rapid development of online retailers who have attracted increasing people favoring online shoppings, which conveniently provides items of interest with personalized experience in our daily life. Leading e-commerce companies nowadays generate hundreds of millions of interactions between tens of millions of users and a huge amount of items every day for a series of prediction tasks, including click-through rate, CTR, conversion rate, CVR, personalized recommendation list, and so on. There is an interesting problem with how to describe the user preference. For example, a user who has bought beach dresses and sunglasses may prefer the topic of trip to beach, in which an item under this topic, such as sunblock, may be clicked. Also, dress and sunglasses may indicate a more extensive topic like outdoor activities at a higher level, in which an item such as sneaks may be clicked. Likewise, an item such as sleeves may attract some users who prefer sports, in which a user such as a sports enthusiast may click. Also, sleeves may attract more extensive users who prefer outdoor activities at a higher level, in which a user such as an outdoor enthusiast may click. In this paper, motivated by the pioneering work, we aim to learn hierarchical representations by bipartite graph to not only exploit the hierarchical high-order connections, but also capture nonlinear interactions for the purpose of applying to a series of tasks, such as user preference prediction and personalized browsing navigation in large-scale e-commerce scenarios. Therefore, we propose a hierarchical bipartite graph neural network, HiGNN, which allows one to stack multiple GNN models in a hierarchical method. It builds a graph as input to the next GNN layer by performing general clustering algorithms on embeddings obtained from the previous GNN layer. The whole process repeats several times until a stopping condition is satisfied. Although HiGNN is a two-stage hierarchical representation learning by combining GNN with deterministic clustering algorithm, which is able to preserve nonlinear interactions and hierarchical high-order connections as well. More importantly, it is easy to scale to a very large real-world application without involving computational expensive metric operation. We summarize the major contributions of this paper as follows. First, we introduce a large-scale hierarchical bipartite graph neural network, HiGNN, which effectively and efficiently addresses the problems of utilizing high-order connections and nonlinear interactions through hierarchical representation learning on bipartite graphs. Moreover, it is scalable to large-scale sparse graph data-related applications. Second, from perspective of supervised learning, by stacking multiple GNN in a hierarchical method, HiGNN is able to obtain hierarchical user preference and hierarchical item attractiveness through the learned hierarchical structure for depicting user and item precisely. Extensive experiments on large-scale e-commerce datasets, both online and offline, show its better preference in a couple of prediction tasks, including CTR and CVR. Third, from perspective of unsupervised learning, we apply HiGNN to automatically generate a topic-driven taxonomy of a large-scale real-world e-commerce for providing browsing navigation with personalized recommendation list to enhance user experience. It not only demonstrates the superiority of HiGNN compared to existing models for placing favorable items into right topics, but also boosts the user preference prediction in terms of precision. We first show the bipartite graph-based loss function, which encourages nearby users and items have similar embeddings, where enforcing that embeddings of disparate users and items are highly distinct. Here shows the loss function of CVR prediction and the full framework of our algorithm. In the offline experiments, we have two datasets. The first one is about common items, and the second one is about new arrival items. The second dataset is more sparse than the first one. We also have 5 different compared methods. HiGNN is a graph neural network method learned 2 neural embeddings for prediction by decomposing neural information into 2 spaces, each of which represents information captured by community level and individualized neural preference, respectively. HiGNN fixed the number of neural levels to 2. DIN is a popular deep neural network method without graph structure information and hierarchical information in the e-commerce system. DIN can be regarded as a special case of our proposed method at level 0. GE is a single-level graph embedding-based method, which is our proposed method using only 1 level without hierarchical information. HOP only is a submodel of our proposed method, which considers hierarchical neural preference only, without item attractiveness. HIA only is a submodel of our proposed method, which considers hierarchical item attractiveness only, without neural preference. We use AUC as the evaluation metric. It shows that our proposed method significantly outperforms the baselines in all 2 datasets in terms of AUC. In particular, GE is better than TIN, which indicates that the graph embedding method is able to represent the neural preference and the item attractiveness more precisely. Both HOP only and HiGNN consider neural hierarchical embedding without item hierarchical embedding. Because HiGNN fixed the level to 2, it is relatively worse than HOP only. Our proposed method performs better than HOP only and HIA only, which indicates that either the neural hierarchical embedding or item hierarchical embedding is effective for CVR prediction model. Moreover, the proposed method performs best among all compared methods, which indicates that the combination of hierarchical embedding of neural and item can further improve the CVR prediction accuracy. A more important thing we observed is that HiGNN still works on very sparse dataset. For example, the cold start scenario. Notice that HiGNN outperforms DIN better in Taobao dataset 2 than Taobao dataset 1. It shows hierarchical information works more effectively when the graph is sparse. In the online experiments, we use 4 evaluation metrics. UV is unique visitor, the number of different clicked visitors, indicating whether our recommendation can attract users to click. CNT is transaction count, the number of transactions indicating whether our recommendations can increase sales volume. CTR is the ratio of click number to visit number, one popular evaluation metric in e-commerce system, especially in search and recommendation scenarios. CVR is the ratio of transaction number to click number, which directly show the recommendation effectiveness on sales order. We apply our model on the real Taobao e-commerce online system for new arrival products to solve the cold start problem. Table 4 reports the results of improvement of UV, CNT, CTR, and CVR on 2 testing days. The results show that our proposed method increases commercial values under all e-commerce evaluation metrics. Both CNT and CVR, 2 important metrics reflecting the sales volume, are improved by more than 2% on 2 A/B test days. Moreover, HiGNN also increases UV and CTR, which indicates our proposed method can achieve user preference and item attractiveness more precisely and attract more visitors to click their interested items. Now, we briefly introduce hierarchical bipartite graph neural networks for e-commerce taxonomy. User search queries can effectively reflect the topics of interest to the user to bridge the gap between item taxonomy and user search intention. We apply our HiGNN on the query item graph to automatically generate a new topic-driven taxonomy structure. Here we modify the user item bipartite graph to query item bipartite graph and also modify the loss function for the bipartite graph. We show a taxonomy case generated by our method from the real-world Taobao dataset. We apply our method to generate a 4-level taxonomy, and each parent topic is split into several children topics. We also find some interesting topics, such as quit smoking clean-ups in male care topic, which are not existed in other taxonomy generated by the compared algorithm. That's all for our work. Thank you.
Okay, since the presenter is not here, we have to skip the question part. So, so next presenter is Chonggang Song from Tencent. He's going to talk about the work LOSEC, local community-based edge classification in large online social networks. So this is a joint work between Tencent and the National University of Singapore.
Hello everyone, this is Chonggang from WeChat Tencent. It is my honor here to introduce our work, Local Community-Based Edge Classification in Large Online Social Networks. This is a joint work with Chen Ling from the National University of Singapore. First of all, I would like to introduce the WeChat social platform. It is the biggest Chinese social platform with more than 1 billion active users per month. It also has hundreds of billions of user friendships. It also has a rich ecosphere. It has a messaging function, content sharing platform where users can post up their timelines and can see their friends' timelines. It also has a payment function where users can pay in both online and offline stores. It has a games function where users can log into multiple games using their WeChat accounts. In this paper, we focus on the relationships in WeChat. In WeChat, relationships often imply real-world relationships. Based on an online user survey that we conducted, we find that around 40% of these edges are placed between colleagues. More than 20% of the edges are placed between family members, and around 10% of these edges are placed between schoolmates. For the rest, there are relationships between users who share common interests, users who do business together, or the relationship between salesperson and their clients, and around 7% of these relationships are not given due to privacy concerns. We believe that knowing the true relationship between users can often benefit many social applications, just like advertising and recommendation. Now that we know the edge classification problem is important in WeChat, we have surveyed the existing works on edge classification in large online social networks. There are basically two types of algorithms. The first type is label propagation algorithms. We realize that such algorithms often require the entire network to have around 50% of edges with ground truth labels. However, in WeChat, from our online surveys, we can only collect around 0.1% of ground truth labels. And then we turn to supervised learning algorithms, where each edge is given a feature vector, and then we put it to a classification algorithm, and it will give us a prediction result. However, we find that the user interactions on WeChat are often very sparse, so that for a large percent of these user pairs on WeChat, they do not have any interaction at all. For most edges, the feature vector would be empty, which is not usable in any classification algorithm. In the below example, we have taken a look at the names of the groups that two users reside in. If the names indicate they are classmates in a certain school or colleagues in a certain department in some company, we would label their edges accordingly. And we find that using this rule-based mining method, the precision is actually rather high. However, the recall is extremely low, which indicates that such features are effective, but in WeChat, these features are extremely sparse, so we cannot directly generate features for edges and place them into a classification algorithm for prediction. In order to conquer the difficulties, we have taken a look at the ego network of a surveyed user. In this ego network, shown in the picture on the right-hand side, we have labeled out the friends that are of different social types. So as we can see, users who are connected with each other closely are often of the same social type. And this motivates us to think we can actually aggregate users from a closely connected community in order to generate dense representations for this community. With this motivation in mind, we have developed our algorithm called LOCEC, which is the Local Community-Based Edge Classification Algorithm. It solves the data sparsity problem as well as the scalability problem with three phases. In the first phase, we divide the entire network into multiple ego networks. In each ego network, we perform community detection, which generates the local communities. In the second phase, we perform the local community classification, which classifies each local community into a predefined social type. In the third phase, we perform edge labeling by comparing the results of the local community classification in phase 2 between the two end nodes of each edge. First of all, let's take a look at the local community detection phase. In this phase, we divide the entire network into many ego networks, and then we identify the local communities in each ego network. And users that are located in the same local community are often of the same relationship type to this ego user. Given the example below on the left-hand side, this is the entire network. if we want to extract the ego network of user 1, then we can see that U1, U2, U3, U4, U5, and U6 are extracted out. And from the picture in the middle, we can see that U1 is then taken out from this ego network before we do community detection. So in here, we would want to remove U1 as well as its incident edges from the ego network. After that, we perform community detection, and we have C1 and C2, 2 local communities. With local communities detected, we want to classify these communities into predefined social types. So for each user in the local community C, we can represent it with a feature vector FU, IUC. In here, FU is a representation of the user's own attributes, such as age, gender, interest, and so on and so forth. And IUC represents the interaction between this user and other members in the same local community. So in here, IUC is defined as aggregation of the ratio of interaction between user U and other members in C. Now that we have the representation of each user in C, we can now aggregate this representation into a feature matrix. However, there are many nodes in the local community, and we want to decide the order to place their feature representation. In our paper, we want the important nodes to be ranked at the top of the feature matrix. So we defined a tightness value using the equation below. If this user is connected with more friends in this community, then it will have a higher tightness value, and it will be ranked at the top position in this feature matrix. With the feature vectors ordered, we can now extract the top k users feature vectors to form the feature matrix of each local community. And given the feature matrix, we can develop a convolutional neural network-based classification algorithm called COM-CNN. The structure of the COM-CNN algorithm is given in the picture below. So basically, it has 3 convolutional components, which are white, square, and zip. These components, we believe, can extract the meaningful information that we need in order to classify each community into predefined social types. Besides COM-CNN, we have also utilized a simpler algorithm for community classification, which is XGBoost. For each community, we take the average and standard deviation of users' features to generate the community's feature representation. After classifying the communities, we can now decide the edge labels. We compare the classification results of the local communities that these N nodes reside in. If these N nodes local communities are of the same type, then we decide this edge is also of the same type. However, if they are not of the same type, then we need to perform another classification step. In order to do that, we need to construct the feature representation of each edge. And this representation is given by the tightness values between the N nodes and their local communities, as well as the softmax distribution of these local communities' social types. With this feature vector, we train a logistic regression model for label classification in order to determine the label of each edge. Next, we perform experiments in order to see the effectiveness and efficiency of our proposed low-sec framework. These experiments are carried out over a subgraph that is extracted from the real-world WeChat network. This subgraph contains more than 42,000 nodes and 1.1 billion edges. Among these edges, around 431 edges are labeled with ground truth. We compare our algorithm with the following baselines, which are PropWB, which is a label propagation-based algorithm, and Economix, which is a matrix factorization-based algorithm, and XGBoost simply uses the features for each edge for classification. For our proposed framework, LOSEC, we have developed two algorithms, LOSEC XGB and LOSEC CNN. LOSEC XGB uses XGBoost algorithm in the community classification step, and LOSEC CNN adopts the COM-CNN algorithm in the community classification step. As we can see from the table on the right, LOSEC CNN performs the best, with LOSEC XGB being a close runner-up. In this set of experiments, we want to vary the ground truth percentage from 5% to 80% of all the edges that are labeled with ground truth. As we can see from the pictures below, supervised learning algorithms rely less on ground truth labels than label propagation algorithms. As we see, PropWB increases the most as the percentage of labeled edges increase. And LOSEC CNN and LOSEC XGB are not so sensitive to the labeled edges percentage. And LOSEC CNN performs the best in all four sets of experiments. Next, we have performed LOSEC CNN on the entire WeChat network with hundreds of billions of. Now, let's first take a look at the distribution of community and relationship types. As we can see, for community, around 50% of communities are actually family members, around 31% are colleagues, and around 20% are schoolmates. However, for the relationship type distribution, we see around only 35% of edges are family members, and around 47% of edges are colleagues. So as we can see, for family member relationship, when it comes to community, there's a large number of communities that are family members, but when it comes to relationship, the proportion decreases from 49% to 35%. On the contrary, for colleagues, when we look at community types, the percentage is 31%. However, when we look at the relationship types, the percentage is actually 47%. It goes up a lot. And this is because many of the colleague communities are very large, with more than hundreds or even thousands of users in one local community. However, the family communities are not so large. They're often composed of around 20 or 30 users. So that explains the difference in this distribution. Also, we have applied our LOSEC CNN results in advertising. So in this set of experiments, we have two advertisements. In the furniture advertisement, for LOSEC CNN, we have placed the ad among users who are family members of each other. And in the relation strategy, we have simply placed the ad in the same number of users who are just friends with each other. And we can see the LOSEC CNN performs much better than the relation strategy. For the mobile game, in LOSEC CNN, we have placed the ad between users who are schoolmates of each other. And the result is very similar. We have seen a large margin of increase in the click rate and even a larger margin of increase in the interact rate. So that's all for my representation. Thank you all for listening. If you have any questions, please feel free to drop me an email. Thank you.
Okay. So is there any questions? Let me see. Okay, seems no questions. So I have a question for the presenter. So I see like in the experiment, I only see like the results on communities based on like colleagues or family or schoolmates. So what about those less popular, relationships, like, like the community based on common interest or based on business relationship? How does the algorithm perform on those type of communities?
Well, for our work, because we first before we do anything, we want to know what are the major types of relationships in this network. So we conducted a user survey, and the results show that the major types like colleagues, family members, and schoolmates consist around more than 80% of these edges. So that's what we focus on in this work. And the types that are not so popular, such as users who share common interests, we have basically put them into the other types that we will be working on in our future work.
I see. Thank you. Okay, so next we will move on to our last presentation. So the presenter is Jiaping Gui from NEC Lab. The work is APTrace, a responsive system for Agile enterprise level causality analysis.
Good morning, everyone. This is Jiaping Gui from NEC Labs America. The title of our paper is APTrace, a responsive system for Agile enterprise level causality analysis. Here is the motivation of our paper. As you know, the threat detection and investigation is an important security solution in enterprises, especially from the commercial solutions from Cisco and Symantec. Among these solutions, there is an important technique called the backtracking analysis. It helps investigate the root cause of complex security attacks. Here is the typical process. First, the agents are installed on different types of operating systems, such as Windows, Linux, and Mac operating systems. These agents will then monitor the status of the system and collect the data about the status. The information will be stored in the database. So during this process, there is a defense system constantly monitoring the database. So if there is any suspicious behavior happening in the database, then an alert will be triggered and sent to the security analyst. And the security analyst will further investigate how this attack, suspicious behavior happens. So the backtracking analysis is applied to the last step, the investigation step. And the starting point is the malware that triggers the malicious behaviors and the alerts to the security analyst. So as you know, for the malware, the behavior is happening in the direction from top to bottom. However, the backtracking analysis is to find the root cause. So the direction is from bottom to the top. Here is a concrete example of our motivation. So here we use a phishing email attack that uses the Windows privilege escalation vulnerability. So in this attack, the attacker first sends an email to the victim, and the victim opens the attachments in the email. This step will create and execute the malware embedded in the attachment. During the execution of malware, it will scan the whole system to obtain the sensitive information, such as the password. After getting the password information, the malware will inject the malicious code into a file that is executable. And during the execution of this malicious code, it will access the sensitive database. So the bottom figure draws the whole process of this attack. As you can see, there are two areas. One is shaded and the other not. The shaded represents the benign area, benign steps, and the unshaded represents the actual malicious path. So as you can see, the access to the sensitive database is the alert point that is triggered and the notification sent to the security analyst. To find the root cause of this attack, we need to use backtracking analysis. And there are two different directions. As you can see, if we go backwards, all the steps from the starting alert point. So one direction is to the top directly, and the other direction is go to down first and top next. So the other direction you can see will traverse all the passes in the benign area. So this can trigger a challenging problem, that is the explosion problem. Because if we do not use the heuristics, then the whole backtracking analysis will explore a lot of relevant but benign system events. This will not help the backtracking analysis. And also the existing solutions, they have their limitations because they are based on the heuristics that are case specific. So they cannot be automatically applied. So in the realistic workflow, we need to apply heuristics multiple times until we find the penetration point. However, in this workflow, if we try and verify the different heuristics, then we need to terminate the execution early or set a time limit. So this can lead to either a too small or too large dependency graph due to the imbalanced distribution of system dependencies. To address this challenging problem, we found if we can make the execution responsive, then we can avoid having a too small or too large dependency graph. So here, if we can keep the security analysts updated during the whole process, then we can accelerate the whole process of backtracking analysis. So we designed an interactive process that incorporates the heuristics from security analysts. So first, we allow the security analysts to express different heuristics using a unified framework. Then we provide a responsive backtracking analysis through a technique called the execution window partitioning. Here is the framework we designed. So in this framework, you can see there are three inputs. The first input is the security anomaly alerts. That is the starting point for the backtracking analysis. The second input is the BDL script, is the backtracking analysis language that's used to incorporate the heuristics from security analysts. The third one is the system log history. This history records the system activities in the database. This is a concrete example of BDL script. As you can see, in this script, the grammar is similar to the SQL query. However, this script is designed specifically for the security query. So you can see we have the time, duration, and the host range, and the keyword backward, and also three different types of events: file, process, and IP. And we have the conditions to make the execution conditions met. And we have the output file for the backtracking analysis. Now I'm going to explain each of the key components in the framework. The first component is called the refiner. It processes the BDL scripts and generates the metadata. So the metadata means the executable instructions and parameters to run backtracking analysis. And the second component is the key component of our framework. It executes the backtracking analysis progressively. So there are two steps. First, it searches the system logs with the execution window partitioning algorithm so that they can progressively update the dependency graph. And the second, it relies on the dependency graph maintainer to realize the certain types of heuristics. So here we try to prioritize the different heuristics so that we can accelerate the backtracking analysis. To evaluate our framework on the real-world system, we have several metrics. The first one is the necessity of responsive backtracking analysis. Here we try to answer two questions. First, the severity of dependency explosion, and the second one is the difficulty of setting right time limits. So for the first one, so we randomly selected 200 events from database, and we found the execution time of about 36% of events. Their execution time is over 2 hours. And regarding the dependency graph, the size can be over 5,000 events for about 20% of events. And the maximum size can be over 30K events. So regarding the difficulty of setting right time limits, we set the time limit from 1 minute to 30 minutes. And the button on the right side, the figure on the right side shows the results. As you can see, in each box plot for each time limit, we cannot see a clear distribution. And also, we found that the top 10% of points, the execution time is about 3,000 times larger than the bottom 10%. So you can see the distribution of the execution time is not fixed, it's dynamic. So it's very difficult to set a right time limit in the real world system. The next metric is to measure the usefulness of APTrace in real-world attack cases. Here we use the 5 real-world attack cases to evaluate the APTrace. So here is the results. You can see from the table, the third and fourth column shows the size of dependency graph. No optimization is the baseline, and optimization means our solution. You can see the size of dependency graph is significantly reduced. And we also recorded the number of heuristics applied and the total execution analysis time. So you can see the number of heuristics and the total execution analysis time is acceptable and significantly less than the baseline. The next metric is to measure the responsiveness of APTrace. Here we tried to answer the question, how long people need to wait between 2 consecutive updates. So here we show the results in the table. You can see we compare the hours framework with the baseline, that is the backtracking analysis without any optimization techniques. So we recorded the average time, the standard deviation, and also 90, 95, and 99 percentile of execution time. So we can see our framework can achieve much better results than the baseline. Especially, the APTrace can reduce the 99 percentile of execution time by 57 times compared to the baseline solution. This means in our solution, the security analysts don't need to wait much time for the next update. The next metric is to measure the efficiency of APTrace. Here we try to measure both the CPU and the memory usage, and the figure shows the results. As you can see, in terms of both CPU and the memory usage, the stable usage is around 11% and 3% respectively. So here means both CPU and the memory usage are acceptable and applicable in the real-world application scenario. In conclusion, we designed APTrace, a responsive system for Agile enterprise-level causality analysis. To do it, we designed and implemented interactive backtracking analysis by abstracting analysis heuristics in a unified framework called BDL scripts and returning partial results of analysis using execution partitioning window algorithm. Especially, we evaluated our APTrace system in the real-world attack cases, and we found APTrace can achieve very promising results. In particular, we found that APTrace can reduce the top 1% longest waiting time between 2 consecutive updates by about 60 times compared to the baseline solution. That's the end of my presentation. Thank you.
Okay, so any questions? If not, I have a question. Very interesting work. So from my understanding, it seems the entire search process is interactive. So let's say if I add some new heuristic patterns, is the new search process incremental? What I mean is you only search search for the new patterns added, or you search all the patterns added so far?
Yeah, this is a good question. So actually, we, as you mentioned, so we use the incremental search process. We have the dependency graph maintainer, so components. It records all the previous searching graph, and then we can directly use based on the earlier graph to do the next query process.
I see. Also, like you mentioned, like during the search, you prioritize certain heuristic patterns. Like how do you determine the priority of the patterns?
Yeah, so here, so is more like, so, you know, in the system, so different events, they can be executed in different orders. But for some events, they can be executed multiple times. So how can we ensure that the same event can be avoided? I mean, can be, for example, pre-event A to event B, and event A to event A can be to event C, B and to C. So if we can maintain the order like A, B, C, not A, C, B, like this way, then we can ensure the order can be more efficient. I mean, the whole process will be guided. So
I see. Thank you.
Sure.
Yeah. Okay, so seems we are finishing a little early. So okay, thank you everyone for joining the session. I hope you enjoyed the session. Have a good day.
Thank you. Have a good day.
Yeah. Okay, so Shamila, Xiaodi, I'm gonna logging off.
Okay, thank you.
Yeah,
Hi.
thank you very much.
Right.
Very nice working with you guys.
Thank you.
Okay, bye.
And Shadi, you are still there? Shadi, are you there?